In this video, we're going to talk about section 11.2. I had mentioned in another video that there are 4 options for solving a system of equations, and we've looked at 3 of the 4 already. They were graphing, substitution, elimination, and then the 4th one to know is matrices. There's a definition. A matrix, or a coefficient matrix, is a table of numbers that are arranged in rows and columns. The plural of matrix is matrices. Okay, so for example, suppose that we have a matrix, matrix A, and I'm using square brackets. You could also use a rounded brackets to enclose the table of numbers. Usually we use a capital letter to denote a matrix, although we can really call a matrix anything that we want. Capital letters are usually used, though. One of the things that we sometimes care about when we're working with a matrix is the size of a matrix. The size of a matrix is characterized by the number of rows and the number of columns, and it's got to be in that order. Okay, so here's 2 rows, 2 columns. This would be a 2 by 2 matrix. I've got some other matrices here, matrices B, C, and D. Matrix B would have 3 rows and 2 columns, so this would be a 3 by 2 matrix. Matrix C would be a 2 by 3 matrix, 2 rows, 3 columns. Matrix D would be a 1 by 2, there's 1 row and 2 columns. Why do we have matrices? Well, the topic is systems of equations, and an augmented matrix can be used to represent a system of linear equations. Here's an example. Suppose that we have this system of linear equations, 2 equations with 2 unknowns. Now, in an augmented matrix, the rows represent the equations and the columns represent the variables. So in the first equation, I've got a 7 in front of x, a 1 in front of y, and then a -6 in the coefficient side. In the second equation, I've got a -2 in front of x, a 13 in front of y, and then a 5 on the coefficient side. Now, a coefficient matrix, that's what I was talking about up here, is different from an augmented matrix. Notice how in this matrix we have a vertical bar. The vertical bar represents the equal sign, and that's a necessary thing that we need in an augmented matrix. If we did not have the vertical bar, we would be describing a coefficient matrix, or just a plain matrix, and there's no direct connection to systems then if you don't have that. Okay, so it's a notational thing. Here's another example. 3 equations, there's 3 unknowns, and so my first row, I've got a 1 in front of x, a 3 in front of y, a 2 in front of z, and a -1 on the coefficient side. Row 2, there's a 2 in front of x, a 5 in front of y, a -1 in front of z, and a 2 on the coefficient side. And in the third equation, there's a 3 in front of x, a -8 in front of y. 0 is in front of z. This would be kind of an unsimplified deal here. You'd want to subtract 4 from both sides. And -7 then would be in the coefficient column. Okay. Here's going the other way. So like if we had a augmented matrix as a system, in the first equation you're going to have 5x minus 3y equal 4. The second equation, -1 times x plus 4/3 times y equals -6. Over here, this would be representing a 3 by 3. So I'm looking at 2x minus 7y minus z equals 0. And then 3y plus z equal -1. And then -5 plus 9z equal 3. The next thing that we'd want to know is various operations on a matrix. There are 3 row operations that we're allowed to use. The first one, we can switch any 2 rows, and if you think about this with a system, if you have a system, you can switch any 2 equations, and that's not going to matter. You still have the same group of equations regardless of what order they're in. The second one, you can replace a row by a non-zero multiple of that row. Again, if you think of that in terms of a system, if you have an equation, you can multiply both sides by a number as long as it's not 0. And in the third one, replace a row by the sum or difference of that row and a constant non-zero multiple of another row. Okay, in this third one here, I'm basically describing that the elimination method is okay to use in matrices. That's exactly what we were doing when we were describing the elimination method. We're adding equations together. Sometimes we got a multiple that we got to use in the equations when we add to eliminate a variable. Here's an example of a row operation on this matrix. Now, a capital R is going to represent a new row, and a little r is going to represent an old row. This is notation that you'll see in the book. And so basically in this calculation, I'm going to get a new row 2. Row 1 is going to stay as is, and I'll get a new row 2 here. To get the new row 2, I'm going to take negative 3 times row 1 plus row 2. So let me go ahead and do that now. Negative 3 times 1 is negative 3. Plus 3 would be 0. Negative 3 times negative 2 is 6. Plus negative 5 is 1. And then negative 3 times 2 is negative 6. Plus 9 is 3. So here'd be my new row 2 then. Okay. Next thing is the definition. A matrix is in row echelon form when three things happen. Item 1, any rows of all zeros are at the bottom. If you come into a calculation where one of the rows is all zeros, go ahead and pull that to the bottom. Item 2, the first entry from the left in each non-zero row has to be a 1. Okay, if it's not a 0, you got to see a 1 there. Item 3, each leading 1 is to the right of all leading 1s in the rows above it. Okay, so here'd be some examples of some matrices that are in row echelon form. Basically what you're looking for is 1s down the diagonal and 0s in the lower triangular part. Okay, we have to have a 1 leading off if the numbers are not 0. Okay, now any row above that has to have a 1 that is to the left of that 1 that is right below. And so here'd be some other examples of some matrices that would be in row echelon form. Now, when we solve a system, we use what's called the Gaussian elimination method. Basically, what we mean by that is we're trying to get the matrix into row echelon form. Again, that just simply means 1s down the diagonal and 0s in the lower triangular part. Okay. So here's an example. I want to solve this system by using matrices, or what's called the Gaussian elimination method. Same thing, matrices. And so, of course, the first thing I need is a matrix. Okay, here would be the augmented matrix representing the system that was given. Now, the idea is I got to get this matrix here into row echelon form. So we're looking for 1s down the diagonal and 0 in the lower triangular part. Once we are in row echelon form, we're going to convert back to a system, and at that point we should know one of the variables, okay, or we should know the answer. So let's go ahead and do that now. Now there is an order to this. Okay, you want to get the columns set as you go along. So get column 1 set, and then get column 2 set, and then get column 3 set, etc. Okay. Step 1 is to get a 1 in the upper left-hand corner. So right now I've got a 2. If I switch row 1 and row 2, then now I've got the 1 in the upper left-hand corner. Now, right below that, I need a 0. Okay, so I need to do some row operation on row 2. I need a new row 2 where I've got a 0 leading off there. Okay, now to get this 2 to turn into a 0, you can take negative 2 times row 1 plus row 2. Row 1 is going to stay as is, okay, and I'm going to get a new row 2, like I said. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times negative 4 is 8, plus 5 is 13, and then negative 2 times 9 is negative 18, plus 5 is negative 13. Column 1 is now set, and the next thing would be to get this 13 to turn into a 1. Again, I'm trying to get 1s down the diagonal. I have a row operation that allows me to just simply multiply a row by a number, and so that's what I'm going to do next. I'm going to take row 2, which is going to be new now, and I'm going to multiply the old row 2 by 1/13. 0 times 1/13 is 0. 13 times 1/13 is 1. Negative 13 times 1/13 would be negative 1. So now at this point I'm in row echelon form, and I'm going to convert back to a system. I've got 1 times x minus 4 times y equals 9 for the first equation, and then the second equation, y equal negative 1. So I know one of the variables, y is negative 1. To get x, I can then work backwards, knowing that y is negative 1 means that x would be 5. So the solution to this system would be x equal 5 and y equal negative 1. Of course, I could check that. 10 minus 5 is 5, that's true. And then 5 plus 4 would be 9, that's also true. Okay. Now, just an observation here, if we have a 2 by 2, typically matrices aren't really the option to use. I mean, usually if we're given the choice, most people would use either substitution or elimination when solving. Now, if you have a 3 by 3 or bigger, in the last video I was describing a process of using repeated elimination, and that's an okay method. Matrices, I think, would be a kind of a more preferred approach, since you're just working with coefficients and you're not actually writing out equations each time. It can be easier to use matrices instead. So let's look at some 3 by 3s next. Here's another example. I want to solve this system. And so the first thing is I need an augmented matrix. Okay, and so I've got that set. Now I need to get this matrix into row echelon form, meaning 1's down the diagonal and 0's in the lower triangular part. Okay. Again, I've got to get the columns set. So the first thing is to get a 1 in the upper left-hand corner. Right now I've got a 2. If I switch rows 1 and 2, I'll now have a 1 in the upper left-hand corner. Right below that 1, I need 0's here. Now I'm going to do kind of like a two-step in one thing. I'm going to get a new row 2 and a new row 3 where I've got 0's leading off on those 2 rows. To have this 2 turn into a 0, you can take negative 2 times row 1 plus row 2. To have this 3 turn into a 0, you can take negative 3 times row 1 plus row 3. So let's go ahead and get our new matrix. Row 1 is going to stay as is. Row 2, we're taking negative 2 times row 1 plus row 2. Okay, so negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 1 is negative 2, plus 0 is negative 2. And then negative 2 times 1 is negative 2, plus 6 is 4. The new row 3, we're looking at negative 3 times row 1 plus row 3. Okay, so negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times 1 is negative 3, plus 4 is 1. Negative 3 times 1 is negative 3, minus 1 is negative 4, and then negative 3 times 1 is negative 3, plus 13 is 10. Column 1 is now set, and so now we're going to move on to column 2. I need a 1 in the middle of the matrix. Right now I've got a 0, but I see there's a 1 here, so if we switch rows 2 and 3, now we've got the 1 set in the middle of the matrix. And it also conveniently worked out so that I have a 0 right below that. If I did not have a 0, that would of course be the next move, is to have this number be 0. So the last thing is we just need to simply have this negative 2 turn into a 1. If I multiply row 3 by negative 1/2, then I'll have this number, this negative 2 become a 1. And I also won't disturb anything in the first 2 columns. So negative 2 times negative 1/2 is 1. 4 times negative 1/2 is negative 2. I am now in row echelon form, and so I'm going to convert back to a system. Here would be my 3 equations representing this augmented matrix. Z is negative 2. Okay, and so then if I work backwards here, Z is negative 2. I can find that Y would be 2, and X then would be 1. So x equal 1, y equal 2, z equal negative 2 would be the solution to that. Okay, I've got 2 more examples here. The next one, same deal, we're solving a 3 by 3. Here's an augmented matrix representing that system. I've already got a 1 in the upper left-hand corner. So I need a 0 right below, 2 zeros right below that. In row 2, to have this 2 turn into a 0, you're going to take negative 2 times row 1 plus row 2. And then in row 3, to have this 1 turn into a 0, you're going to take negative 1 times row 1 plus row 3. Okay, and again, I'm doing like a 2-step and 1 type deal here to get the column 1 set. Let's get our new row 2. Row 1 is going to stay as is, of course. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 1 is negative 2, plus negative 1 is negative 3. Negative 2 times 1 is negative 2, plus negative 1 is negative 3. And then negative 2 times 6 is negative 12, plus 3 is negative 9. Okay, and then row 3, we need negative 1 times row 1 plus row 3. Negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 1 is negative 1, plus 2 is 1. Negative 1 times 1 is negative 1, plus 2 is 1. And then negative 1 times 6 is negative 6, plus 0 is negative 6. The next thing is we would have to get a 1 in the middle. We've already got column 1 set. I see this 1 here, so we can switch rows 2 and 3 to get a 1 in the middle. I've done that next. And right below that 1, I need to have a 0 there. Okay, so right now it's a negative 3, so I'm going to have to do something with row 3. And also, I don't want to disturb column 1, so I'm going to have to use row 2 here. If we take 3 times row 2 plus row 3, column 1 won't be disturbed. Let's go ahead and get our new row 3. 0 plus 0 is 0. 3 times 1 is 3, minus 3 is 0. 3 times 1 is 3, minus 3 is 0. 3 times negative 6 is negative 18, minus 9 is negative 27. Now at this point, if we convert back to a system, that third equation would be saying 0 equal negative 27. Of course, that's not true. And so there are no solutions to this system. It would be an inconsistent system. Okay. Here's my last example for the section. We're solving this system here. I've got my augmented matrix. Now, I need a 1 in the upper left-hand corner. Right now it's a 6. There's a couple of different options that you could consider. One would be to multiply row 1 by 1/6, but now you got fractions early on, and that doesn't sound like tons of fun. So a better option would be to take row 1 minus row 3. Let's do that. Okay, so 6 minus 5 is 1. Negative 1 minus 1 is negative 2. Negative 1 plus 1 is 0. And then 4 minus 3 is 1. Okay, now right below that, I'm going to need zeros in column 1. And again, I'm doing a 2-step and 1 deal here. To get my new row 2, let's take 12 times row 1 plus row 2. 12 times 1 is 12, minus 12 is 0. 12 times negative 2 is negative 24, plus 2 is negative 22. 12 times 0 is 0, plus 2 is 2. 12 times 1 is 12, minus 8 is 4. To get a new row 3, we'll take negative 5 times row 1 plus row 3. So negative 5 times 1 is negative 5, plus 5 is 0. Negative 5 times negative 2 is 10, plus 1 is 11. Negative 5 times 0 is 0, minus 1 is negative 1. Negative 5 times 1 is negative 5, plus 3 is negative 2. All right, now the next thing would be to get a 1 in the middle of the matrix. Right now it's a negative 22. If you multiply row 2 by negative 1 over 22, you'll end up getting a 1 there. And so here's my next matrix. Right below the 1, we need a 0. Right now it's an 11. So I'm going to get a new row 3. If we take negative 11 times row 2 and then add that to row 3, we won't disturb anything in column 1. So here's my new row 3, which is all zeros. Now, when I convert back to a system, of course, the third equation would be 0 equals 0, which is not news to us, but it's a true statement. So in this problem, we would have a dependent system. There are infinitely many solutions, and here would be my answer written as an ordered triplet. Okay. That's it for the chapter. Here's the homework problems in section, that's it for section 11 too. So here's the homework problems there. Be sure to look at those.